Dear DSA students, we are so excited to be on this journey with you, and we want to say a big well done for your commitment and enthusiasm so far. Whether you have just joined or you have been learning with us over the past few weeks, we see your progress and we are rooting for you all the way. Now, we know there's been a bit of silence around the learning management system, and we sincerely apologize for that. But here's the good news. We have an update as regards the learning management system, and it is one you'll love. Some of you may have been onboarded on the previous LMS, but want to ask that you kindly disregard any previous link, platform, or communication concerning that old system. We are officially switching to a new platform that you may be familiar with, Canvas by Instructure. For those new to Canvas, don't worry. A video tutorial will be uploaded to guide you step by step on how to use the platform effectively on our YouTube channel. You will also receive an onboarding email directly from Canvas by Instructure to help you get started. Please follow the instructions in the email and input your details to begin your learning journey on the platform. We are committed to making sure your learning experience is smooth, interactive, and impactful. So please, pay close attention to the announcements coming right after this video for more details. We are so glad to have you with us. Keep going, we've got this.
Okay, that's good. I believe it's fine now. Hello, everyone. Okay, good to be back. Sorry for the break. Yeah, so today we're going to be starting with sorting algorithm. And apologies for the delay. It's for the best, actually, because today's class is going to be fantastic. Okay, now, thank you all for your patience. Okay, so today we're going to be starting with sorting algorithm. Okay, in your last class, can somebody remind me what we did in the last class? What we did in the last class, something that you took home in your last class, can you remind me, please? Awesome. I've seen somebody's message. Adedeji said big O notation. Very good. Very good. That was the response I was waiting for, because today we are going to be building on that big O notation. Okay. Now, today we're going to be covering these topics. What is sorting algorithm, right? Why do we need to learn different sorting algorithm? Then we'll understand the types of algorithm that we have, and also cover 17 sorting techniques. Okay, all right, let's dive in. What is sorting? Sorting, in a simple word, is arranging data in specific order. Okay, either you're doing it by ascending or descending. Okay, it is one of the most fundamental operations in computer science, and it is used in many real world applications like your phone contacts, your library books, your student record, and even shopping items. You know, when you want to filter your some shopping items by their prices, by their sizes, depending. Okay, why are we learning this different sorting algorithm? There must be a reason. And different algorithms work better for different situations. And that is why you need to know a lot of them, so that you can know the one to use at that particular time. Then you need to also understand the trade-offs. The trade-offs are like the pros and the cons. So it will help you to choose exactly the correct algorithm for that scenario. We'll dive into it more into the class and you understand better. It also improves our problem solving skills. When you look at it, you realize that, oh, our problem solving skills are always in the manner of, if you are able to sort, the better you can sort, the more you're able to resolve an issue. If I do this, then I get this, then it will result to this. Else, let me do this, right? And that process, that combination of process, is how sorting algorithm works. Okay. Then it is also a common topic in technical interviews. So most of the time, you will always have sorting algorithm as your test questions or interview questions. And that is why it is always important to understand the basics of this class. Okay, what are the types of sorting algorithm that we have? We have the comparison sort and we have the non-comparison sort. All right. Now, today we are going to start with the comparison sort because it is among the easiest of the sorting algorithm. So we will start with that. And the first on that comparison sort is bubble sort. Okay, bubble sort is the simplest sorting algorithm, and it works by repeatedly swapping adjacent elements. Like the way bubbles rise to the surface. And it is best for small arrays or nearly sorted data. So when you're talking about array of maybe 10 items, you can use bubble sort. Or 10 items, one is not far from 10, and that is why it says nearly sorted data. So but in scenarios where you are having items like 1, 500, 20, 1 million in an array, it is not nearly sorted at all. And in that case, it will be a very terrible algorithm to use. And the time complexity for bubble sort is 0n². I'm sure you were taught that in your class yesterday. Now, I would like to explain this bubble sort in a more simpler manner that everyone would understand. Okay, let's take, for example, having children that compare their numbers with the person next to them. So you have some children on a line, right? And then you give them numbers to compare. Okay, now the first child looks at their number and the second child also looks at their number. And if their number is bigger, they swap. So let's say the first child on line 1 on the first item is what? 4. And the second child is 2. What happens? They will switch. Why? Because 2 is less than 4, right? Okay. Then when 4 gets to the next point, what happens? It says the third child is 1. Is 1 greater than 4? Yes. So they swap. So they keep swapping like that until what? Until they get to the last item. And this continues until the biggest number gets to the end of the line. Then we start again from beginning. But this time, we don't need to check that last child again, right? All we just need to do is, we already know that it's the biggest number, so we keep swapping until the value before that last one. And then again, the value before the last one that comes before the last one. And it goes on and on like that. Now, I'm going to give you a visual representation. There was something that was shared in that class. It has been shared on the LMS platform where there's a zip file. I'm sure you all have access to it now on your Visual Studio Code. Okay. Now, we are going to have a look at it. Please respond in the chat session if you have this kind of view with you. If you have this kind of view, please respond in the chat session so you can follow with me. Okay. Now, remember we installed some extensions in our previous classes. We are going to make use of that extension now. So when you right click, you open in default browser. And what happens? We have this view. So it's a little bit of a pet project where all we just need to do is visualize the explanation. If you don't have it, it's okay. It's on the LMS platform and you can just follow through. It is better if you watch with me and then you can go ahead to practice later. Okay. Now we are working with bubble sort. Okay. Now we have this item. right? There are different values in the array. They are like objects in this array. And then let us look at how the sorting works for bubbles. Now, can you see the two items? The image keeps switching. For every one of them, it swaps it. When it sees that the one on the right is lower, it swaps it to the left side, and until it keeps doing that for everything. Okay. And when we look at it, we realize that it does that until the whole system is settled. Okay. If you are following me, say yes. Okay. All right. Wonderful. Now that we have seen the visualization of it with the explanation, I'm sure you understand it a bit more. The more you learn it, the more you get familiar with it and you understand it better. Okay. Now, I would like us to go through the code and also see how it works. Now, this is the code for that running system. You can see there's a for loop that checks the length of the bar, and then it runs another loop in it that checks the length minus 1, the minus I, then minus 1. So that is the I in this first for loop. And this is why it is important for you to understand the way it works, so that when you're looking at the code, you can have an idea of what it is. Okay. Now it checks if it is running, and then it draws the bar. And if the bar is greater than the bar plus 1, what happens? It does its magic. And that is simply what bubble sort is all about. You have access to this code on your laptop, so you don't need to look at mine. Just get your own and unzip the file and go through it as well on your own system. Okay, let's move on to the next one, which is what? Insertion sort. What can we say about insertion sort? It builds sorted array one element at a time. It is efficient for small data or nearly sorted data, just like the previous one. It's like sorting playing cards in hand. You know all those playing cards that we play. And it is best for streaming inputs, online data. You know, we are currently streaming on YouTube, right? So, and the worst scenario is for large random data set. The time as well is 0 and 2. I would like to explain again how this thing will work if we want to break it down. So, insertion sort is like organizing a hand of cards. You start with one card in your hand, then you pick up a second card. You look at the card that you're already holding. Then you put the new card either before or after the first card, depending on which is greater. Then you pick up the third card again. You look at it. Imagine if you have all those cards that have 2, 4, 8 cards. This is what we're talking about here. You pick up the third card again and you look at the cards you're already holding. You find the right spot to put the new card. And you keep doing this until all the cards are in your hand are in order. That is simply insertion. You can see that you are inserting it. You are looking for it, then you insert it. Then you're looking for it, then you insert it. It's different from that first one where we have to go through everything and keep switching and keep switching. Okay. Now, let us look at the visual representation of insertion sort. I would like to reduce the speed a bit so that you can see it more slowly. Okay. Now, let us start insertion. Can you see the two cards? Then he looks at it. Which one is greater? Switches it, takes it to the front. If he sees another one again, that one, he leaves it, he goes to this one, he switches it. And then he has one particular place where it holds like the last card. So this red one here is like the spot where it has reached. And he keeps switching the other ones until it's done. Then he comes back to this place where it has stopped and starts switching again till the end. And then he comes back to that last one and starts switching again until he sees that everything is sorted. Then he comes to the last one, and that is how it completes this other one. So this last one is like the final point, and then this red one that is on the left side is like the one moving in and trying to do the sorting. And when he sees that everything is done, that is the end of insertion sort. Okay. Now I would like to take you to see what insertion sort is all about here. Okay, let's have a look. So what does it do? It checks for the starting point, and if it is less than the length of the bar, it increments. It gets a key. That key is that red one that's the extreme end. And then it sets a J value that is I minus 1. So it's reversing the case. That's why it's going to the left and not to the right. Okay. Now, while J is greater than 0, what happens? And that bar is greater than the key. What does it do? It keeps running and drawing that bar. And then it keeps reducing J. It's as simple as that. Okay. Let's go back to the next one, which is selection sort. Okay. What is selection sort? How does it work? It works by repeatedly finding the minimum and swapping. So it looks for what is the smallest and then it swaps it. Like selecting the shortest person in a line. Imagine if everybody's on a line and they're like, okay, you know what? Everybody be on a line. Then they're like, no, you go to the front. Oh, you come to the back. No, you are too tall for that place. Move to the back. Exactly. That is how this selection sort works. Because you are selecting that short one and you're moving it until it is done. This one is best when you have memory constrained environment. You don't have a lot of memory. And it is worst for practical large data set. The kind of data set that we're using these days, it cannot work for it. The time constraint also is what? O n squared. Let me now try to explain this selection sort in a simple manner. It's like organizing a pile of toys. So you have a toys that you have packed together. And then you look at the toys and you find the smallest one. Then what happens? You put that toy at the start of the new line. Okay? Then you look at all the remaining toys and find the smallest one again. And then you put that toy next in line. And you keep doing this until all the toys are in line. So you don't care whether you're picking the toy from the back or from the front. All that matters is that size is the next size to the smallest one. Okay. Now, let's go back to our code and try to see what selection sorting is. All right, let's look for selection sorting here. Here we have it. Okay. Now, what we have to do is let's look at the visual representation of what I just explained. All right. It looks at the 3. Then it keeps, that first one, it has kept it. Okay. Then it keeps going again and looking for what? The next one that could fit. Once it searches everything, what did it do? It picked the smallest one and took it to the front. Okay. And then it keeps searching like that as well. And it goes through that middle red one, it will take it to the front. Okay, now it keeps doing that until it is done with the system. So just follow the process. You will see that it has moved the tallest one back behind a bit. Okay, and this is how it keeps moving everything and trying to check for the perfect place to put that particular point where it is. Remember, it is noting where it ended. So it is noting the particular point. The point where it's ended the sorting is on the left-hand side, is the red on the left-hand side. And then the other red is the one that is trying to move and understand the system. Okay. So it is noting the last point of its arrangement. That thing is very important because you're also going to see it in the code. Okay. And once it is done, what happens? It switches the last one as well. Okay. Now, let us go to the code and see selection sorting. Now, we will see here that it checks if it is running. And what next? It checks the loop. Of course, it starts with 0. If the length of the bar -1, then it increments. And then it sets a point. That's the mean IDX here. Remember that point that is red on the left-hand side. Okay. Yes, somebody said rearranges serially. Okay. So now it checks it and then it starts running it. It creates another loop and then it looks for where the index of bar of J is what? Is less than the index of bars itself, of the mean index, which is the I. Do you understand? And then it keeps setting it like that until it is done. So this is the coding format. And that was why I started with that explanation to make it easier for us. Okay. Now let's move to the next one, which is comparison sort. So comparison sort, now we have merge sort. We've been talking about comparison sort all this way. Okay. Now this merge sort, how does it work? From the word merge. From the word merge, you already know. It's like dividing and conquer. It's like you are breaking it and then you're putting it back together. It works by splitting arrays through sorting, then merging. So you first of all split the array. Let's say you have 10 items, you split them into what? Into 2. And then you do the first one first. You sort the first one, then you go ahead and sort the second one. Then it's easy for you to merge both of them together. It's like organizing a library shelf systematically. It is best for linked lists and external sorting. You will do more of linked lists in your next class. And it is worse for memory constraint systems. So when you don't have much memory, please don't use it. Like the time constraint is what? 0n log n. All right. Now I'll try to explain again in a simple manner so that we can understand more. Merge sort is like organizing a pile of toys, right? First, in this case, you know when you have the pile of toys, instead of you picking one by one and trying to look for it, no, you decide to split it into 2. And then you see that the 2 is still plenty. You split them again until you have lots of tiny piles with just one toy. Then what happens? You start putting the piles back together. But now in what? In the order. You look at the first toy in each pile, you pick the smaller one and put it in the new pile. You keep doing this until all the toys are in one big sorted pile. Okay. Now, Let us take a look at the merge sort here. What happens? Let's see. Can you see that it looks through it and then it's supposed to split it into two? So let's just wait and see. Can you see that it did not go to the end? It ended at the middle. It will finish that one first before it goes to the next one. Can you see that when the first half is sorted, then that is when it goes to the what? The second one. Okay. And once it is done sorting both of them, it now merges both of them together to know where the best height is supposed to be. Okay. And it keeps going on and on until it is done. Okay. Now let's go to the next one, which is quick sort. What is quick sort? What can we say about quick sort? From the word quick, it's pivot-based partitioning. Before I proceed, I would like to answer a question from the chat session. Which app are we using to run this program? All you just need to do is right-click on your Visual Studio Code and preview it on default. You can open it using your Chrome or anything. It doesn't need any app. It's a simple HTML file. All right. So for quicksort, it is pivot-based partitioning. It works by dividing array around pivot recursively. Who among us knows what recursive means? Recursive is like picking its own, like there's an inner part of it inside its inner part and its inner part and its inner part. So it calls itself over and over, like organizing a messy desk quickly. And the best scenario is for general purpose sorting. The worst case is for bad pivots, which is very rare. And the time on the average is O(n) log n. All right. Now, let's take a look at quicksort here. Okay, let's see how it works. Can you see that it picked from the two? It started from the front and from the back. Okay, and then it started doing what? Looking at each one of them and then doing the needful immediately. It's not waiting for any response. It's just sorting it out immediately, following that same format that we just explained now. And in so doing, everything would what? Be sorted out. All right. And it continues on and on like that until everything is sorted. All right. Let us go to the next one, which is, heap sort. What is heap sort? It uses binary heap structure. It works by building heap and extracting the elements, like you are removing the tallest trees first. So if you have trees that fall on each other, you do what? You remove the tallest first. It is best for in-place sorting and for real-time system. And it is worse for cache-sensitive system. And the time is what? N log n. Now I will try to explain what heap sort is in a simpler manner for us to understand. Okay, heap sort is like organizing a family of toys. First, we arrange the toy in a special way where each toy is bigger than its children. Now, the biggest toy goes at the top. We now take the biggest toy and put it in a special line because it's the biggest, right? Then we fix the family tree so that it's still in the special arrangement. We now take the next biggest toy again and put it in our line. We keep doing this until all the toys are in our line. This is another way where we can view it and see. All right, let's view it. Let's see how it works. Okay, let us start. Can you see that it didn't start from the front or from the back? It was just looking around and trying to pick the largest. What did you do? You see that it's going to look at the largest one and takes it to that right side. Okay. All right. Then it takes it, it looks at it again. Which one is the largest? Oh, then it takes it again to that right side. And it keeps doing that until everything is completed. Okay. Now, let us go to the next one. Oh, let's check the code. Heap sort. What do we have here? It checks if it is running. It checks the length of the bar and calls it n. Okay? And then, what does it do? Remember that this is recursive. So it calls heapify. All right. Now, this is heapify here. What does heapify do? Recursive is something that calls itself, calls something inside something. So that is what we're doing here. So it checks the largest, it sets the largest, it sets the point for the left, and it sets the point for the right. And it does the check for the left and for the right and for the largest. That is what that heapify is doing. And then it comes here and set I to be equal to a whole number. So we are not picking decimal points. In case our array is maybe 11 or all those odd numbers, it picks a round figure and then it divides it by 2 and subtracts 1. That would be the initial point. And then if I is greater than 0, it reduces that number. And then it calls that our function heapify. Once it's done, it does what? It comes and check again. For the length of bars, I is the length of bars minus 1. Then, if I is greater than 0, it keeps subtracting from that I. So as long as it is not running, what does it do? It keeps returning, it draws the bars, and then what? It sets it just like that. Okay. Now, this is why it's best for us to see the code after the explanation, and you can have an idea of how it works. Even if you don't understand everything, you can understand bits and pieces of the system. Okay, let's move to the next one. Shell sort. It is a generalized insertion sort, and it works by sorting elements with shrinking gaps. It's like quartz to fine sanding. You know that's when you hold a sharp sand in your hand. It is best for medium-sized arrays. So this one is not for small arrays like 10 objects in an array. No, medium size. Maybe you can have 500, 1000, medium size. And it is worse for bad gap sequence when you have terrible gap sequence in between. No, don't use it. And the time complexity ranges from n log n to what? N squared. Okay, now I will try to explain again in a very simple way so we can get it better. Okay, now let's go and look at shell sort. Here it is. Okay. Now, I'll try to explain the shell sort in a simple manner. Shell sort is like organizing a line of children. First, we look at children who are far apart in line. If they are in the wrong order, we swap them, especially in an assembly ground. Then we look at the children who are closer together. And we keep doing this, looking at the children who are closer and closer. Finally, we look at the children who are next to each other. When we are done, all the children are in order. So it keeps doing this until it switches the last part. And then let's take a look at the code for shell sort. All right. It checks if it is running. It also sets n as the length of the bar. All right. And then it creates a loop that says, you know what? Let gap. We do not use J in the sense, but you can actually use any letter you want to replace it. And then we divide it by 2, right? To create like a random, the next, you round it up. You round that number up, all right? And then you divide it by 2. And then what happens? If the gap is greater than 0, then the gap is equal to that match random divided by 2. And then it creates another loop again and checks for the gap. And if I is less than the number of the length of the bar, it increases. And if it is not running, it returns. If not, it creates a temporary value as the index of that bar, and it sets a J value. So if the J is equal to the index of that for loop that you're currently doing, and J is greater than gap, and bars, the index of bars is J minus gap, which is greater than the temp that we have set, then do what? Keep reducing J by gap. And then continue the process. All right. Now, let's move us to the next sorting, which is team sort. Team sort. Now, for team sort, it is hybrid. And it has, that means it follows the style of the merge sort and the insertion sort. It works by splitting data into runs and then merging them. Like warehouse sorting optimization. So you know warehouse, there's so many things in there. How are they sorting? How are they optimizing the sorting? It is best for real world mixed data. And it is worst for highly custom needs. The time complexity is what? N log n. Okay. Let me try to explain team sort. in a simple way. Team sort is like arranging a pile of toys. First, we look for small group of toys that are already in order. Can you see that this one is different? We look for the group that are already in order. Then we keep those groups together. Then we use a special way to combine these groups. That is the merging part. We keep doing this until all the toys are in order. Okay, let's try to see the visual. Let's try to see the visual representation of team sort. Okay, let's try to reset it so that it can be more scattered. All right. You will see that, remember, it is picking small groups. And then what happens? It keeps merging the small groups together. Can you see that this one is picking two each at a time? It takes it, it merges it with the previous one that it has. It goes back again to pick a group and sort it again and merge it. And it keeps doing that until it checks that everything is in the right order. Now let's take a look at the code, at the team sort code. Can you see that it picks a minimum value? It picks a value called min merge. And then what it does is to do what? Set a value for the length of the bars. And then it starts from 0. And if I is less than the length of the bars, it adds the min merge value to it. And then it waits for insert assertion. Remember that we're making use of two formats this time around. We're using insertion and we're using merge. So now, if you go ahead, you will see that we have insertion sort team right here. And what does insertion sort team do? It creates a loop of that value. That's the starting point which you have passed. You pass in the starting point and the end point from here, right? And then, if it is running, what do? You set the key. Then, you set the j to be what? I minus 1, which is that index of that loop minus 1. And then while j is greater than the value that you have passed in as start, and the index of j in the bar is greater than key, what happens? It keeps the settings going. And once it's done with that, it sets this index here for this. Once it is done with this one, it comes back here to come and check if the size now is equal to the what? Minimum merge, or the size is less than n, or the size is equal to the square of the size. And then it also checks if the left, when the left is 0 and left is less than n, let it keep adding the square of the size to left. So that's how it's able to create the middle value, the right value, and then once it is done, you know, it has the left, the middle, and the right now. It now does the merge team functionality. All right. And what happens in the merge team? It sets the value for the left value, sets the value for the right, sets the index I, j, k, it sets the value I to 0, j to 0, and k as the starting point. And then while I is less than the length of the left value, what happens? And j is less than the length of right. It keeps the flow. It keeps adding to I or keep adding to j respectively. And that is how the whole system keep working. Okay, now we have 5 minutes more to the break time for you to fill your sheet. So let's just try to do one more. Before we move on. Let's do cycle sort. All right. What is cycle sort? It is used to write optimized algorithm. It works by rotating elements into position. Like when you are rotating puzzle pieces. It is best for flash memory or SSD disk. I am aware some of us know what that is. All right. Simply memory drives. That's simply what it's best for. And it is worse for general purpose use. If you notice from this class, you will realize that every one of them has what it is best for. So in the scenario where you are considering, use what is best for you. Now, the time complexity is 0n squared. I would once again take us through a simple explanation of cycle sort. Cycle sort is like organizing a line of children. But in this case, for each child, we count how many other children should be in the front of them. Can you see that this one is different? We look at A and we're like, we'll go around and find out how many children should be in the front of A. We put each child in that correct spot, and then we only move each child once. When we are done, all the children are in order. Okay, let's take a look at the cycle sort visualization. Let's try to understand how it works. Okay, now we have this data here. All right, let's assume these are the children. Let's start sorting. Can you see that it looks at that first one and says, okay, you are supposed to be here? It goes around to count how many other children should be in front of that first one. All right. Once it sees it, what happened? Can you see that it has brought it to the front? Okay. And it keeps doing this for each one of them. This makes it very easy to sort for this kind of format. It keeps going through each one of them, one after the other, and then it keeps moving it. And this is how it will do until everything is done. Just try to study the first red and the second red. You will see that there's a point, there's like a standing point, or let me call it turning point, where it's like there's nothing lower than these values in my front again. So let's go and group the rest. All right. And then, yeah. Once we are done with this cycle sort, we will go for our attendance. Now, let me try to increase the speed and just make it faster. Okay, and that is it. It has, let's start again. You will realize that now it is much faster and it sorts everything and voila, it is done. Okay, now that we have done that, let's go through the cycle sort code and see what the code does. Okay, what does it do? It checks if it is running, set the bar as we have always done. It has two loops that is looping through. It also sets a value here for it to know where to start the cycle from. And then it sets the item. And if the item is equal to the bar, what happens? It does the rest. And while the value it has set is not equal to cycle start, it continues the process, creates another loop in it, and while that item is equal to the index of bars, what happens? It increases the POS, which is the cycle start, and then it keeps going on and on until the end. So, well, after the break, we will come back and continue the process where we will talk about the non algorithm. So now we've been talking about what continuous as in where you have to. Now we'll talk about the one that is not like that and it's more complex. Okay, so thank you, and you can check for your attendance now. Okay, I'm aware that the attendance link is yet to be shared. Don't worry, you will get it very soon. The team is working on it to make it ready. Okay, so while we're doing that, let's just continue with the class. And when the link is ready, we'll then go for the break. It's fine. All right. Okay, so now we are going to have a look at comb sort. All right. If you've been enjoying the class so far, can I hear yes? Yes. Even with the challenges, we're still having fun, aren't we? Okay. All right. Great. Okay. So we have comb sort. It's a bubble sort variant. Do you understand? It's almost like bubble sort, but it is not bubble sort. You get me? And it works with shrinking gap, like the 1.3 factor, like removing turtles in early passing. And it's best for moderate sized array. It is worse for bad gap sequences again. And the time complexity is O n squared. Okay, now I would like to take us through the view. All right. But before we do that, let me try to explain comb sort in a simple manner. All right. Comb sort. Let's look at the visuals. Okay. Comb sort is like organizing a line of children. But in this case, the first thing we look at, right, are children who are far apart. If they are in the wrong order, we swap them. We're like, no, this one, no, this one is not supposed to be here. Yeah, swap. You are swapping them. That means the first one, let's say you look at the child on number 2, and then you look at the child on number 10, and the child on number 2 is taller than the one on number 10. What happens? You tell that one on number 2 to go to number 10, and then you bring that one to number 2. All right. If they are in wrong order, we swap them. Then we look at children who are closer. So after looking at the ones that are far apart, we'll come by and look at the ones that are closer now. And then we keep doing this, looking at the children who are closer and closer. And when we are done, all the children will have been in order. Okay, let's have the visual representation of that explanation and try to see how we can get a clearer view about it. Oh, it's too fast. Let me reduce the speed. All right, let's take it slowly and let's open it again. So let's open it and then let's start. Can you see? Can you see what it's doing? You will see that it is switching. Anyone that it picks and is higher, it will switch it. Can you see? It will switch that one now. Can you see? So it will switch anyone that it sees that is higher. It will keep switching and swapping it until the whole thing is swapped and it's working just fine. Now, this system of swapping is that algorithm that it's following to ensure that, okay, this is actually well done. So if they are okay, it doesn't need to swap. If they are not, then you can see now that it's closer because it has ended up swapping most of them, and now most of them are closer to each other. Then it goes back again to see, okay, are you taller than the one in front of you? Are you taller? It keeps checking if there's anyone that is taller than the one at the back. What happens? It switches. And then it checks everything again. And once it sees, it loops through everything and sees that there's nothing to do again, it ends the loop. All right. Now, we'll have a look at the code and try to see the visual representation of this comb sorting. Now we've seen the visual representation, we want to look at the coding, like the code base, what's it all about. All right. Okay. So here we have comb sorting. Okay. All right. So now we try to look for the code. We'll see it once we find it, then we can just come back to here. But it's basically one of the things that we're doing here, right here. So we have those comb sort. What does it do? It checks if it's running, it checks the length of the bar, it checks the gap, and then what does it do? It sets swapped to true. Okay. Now, while the gap is greater than 1, or remember that this signal means or it is swapped. What happens? It sets the gap value to be the gap over 1/3, then it gets the round up value of that number. And if that value that it now gets is less than 1, then it sets gap to be equal to 1. And then it sets swap to be false. It doesn't swap two values at it, like it swaps it one and after the other. All right. Then it now creates another loop. The first one is a while loop. Then the second one is a for loop that now checks when I is 0. If I is less than n minus the gap that we have set, then it increases I. And if it's not running, what happens? It returns. But if it is running, then it sets those values. All right. Now, let's go ahead to our next topic, which is gum sort. But before we go to this one, I would like to address the comment in the chat. I am actually following you, but as I advised in the beginning of the class, the most important things is to understand the class. That is the most important thing. And this class is very complicated, but we're making it as simple as possible. So it is best you focus on the class. If you miss it at any point, because we keep getting, if you realize we started with bubble sort, which is the simplest, and we are going to more complicated parts. So if this complicated part are picking one or two or a variant of the ones we have talked about. So if you don't understand that one, it will be hard for you to understand the ones coming up. And that is why it is okay if you don't understand the code, but understand the logic, and then you can always get better with writing the code. But the logic is something that you need to explain. When they ask you a question, even if you don't know how to code it, but you can explain to your interviewer or your supervisor what you feel it is. It takes you a long way, because when you now know how to code, you will know what you want to code. You already understand what you want to code. So now you are learning the code and you're putting into cognizance what you have learned. And I see now that we have the link, attendance link. It's now in the chatting section. So please feel free to just click on it and mark your attendance. However, I will continue with the class as we are way behind schedule. Okay. Now, what is this sort? What is gum sort? It's simple loop algorithm. It works by swapping backwards when needed. You can see that this one is different. You are swapping backwards. The previous one we did was not swapping backwards. You were just swapping front and back, right? Far apart. But this one is swapping backward, like a garden gum sorting flower pot. Now, it is best for simple implementations and it is worse for practical applications. Now, the time complexity here is what? 0n squared. Okay. Now, we are going to be looking at the simple explanation of gum sort before we go into the visuals. All right. In a simple word, what is gum sort? It's like it's like organizing a line of children now again. But in this case, you start at the beginning of the line. And then you look at two children next to each other. And if they are in the right order, you move forward. If they're in wrong order, you swap them and step back. You keep doing this until you reach the end. All right, now let's try to have a look at the visual. Can you see that it's starting from the front? It does what? It swaps them. And then it takes a step back again. And then it compares the two and swaps them. It takes a step back again, compares the two, and swaps them. And it continues the process. So just watch as the red bars are moving forward and backward. Okay. You will notice that it's moving forward and then it swaps. If it sees anyone to swap, it goes backward. And it keeps going backward until it sees the place to put that particular one that it has swapped. Once it sees where it should put it, what does it do? It goes back again to the front and goes to swap again. Then that smaller one, it keeps going back till it sees where that smaller one fits. Okay, and when it's sorted that one out, what does it do? It will go back again to swap that last one until it sees where it will stay. All right. And once it is done, that is it. It is best for simple implementation. Do you know why? Because we keep going back and forth. Now, imagine if we have 1 million bars. How would you be going back and forth on it? You know? So it will be too ridiculous because n squared, for every n, it is increasing it squared. So 2 squared is what? 4. 4 squared is 16. Can you see that it's just increasing rapidly? So now imagine if you have 1 million, and that is why it's only best for simple implementations. Okay, let's take a look at the code. Okay, let's take a look at the code. It checks if it is running, if that bar was running. It sets the index to be 0. And then while that index is less than the bar's length, it keeps checking if that thing is still running, right? And it checks if the index is equal to 0, it increases that index. I mean, it increases that value, that number. So let's say 0 now, and it sees that, oh, okay, it increases it by 1, and it keeps increasing. Okay. Now, it draws the bar for the bar chart, and then if the index of that bar is greater than or equal to the index of the bar minus 1, it increases the index. Okay. Now, if not, what happens? That's the else function. It reduces the index. All right. And this is the point where what? It sets the bar index, and then if everything is resolved, what does it do? It turns the running to false. And that is why how that graph was moving. Okay. Now, let's move ahead to the next one, which is the cocktail sort. We're still on the comparison sort now. The cocktail sort is bidirectional bubble sort. Can you see now that we are mentioning bubble sort again? So there are some bubble sort is like basics. Then they are now having variants of it. Okay. So now imagine bidirectional bubble sort. What's bidirection? That means like two directions of bubble sort. That's simply what it means. Okay. It works by alternating the left-right passes, like shaking a cocktail mixer. It is best for moderate data with small ranges, and it is worst for large random arrays. It's only best for moderate data with small ranges. The time complexity is also O n squared. Okay. Now, let me try to explain this cocktail in a simple word. Please keep in mind the explanation. Don't mind the code. Don't look at the complexity of the code. Just if you look at that explanation, you will see that it is very relatable. Keep remembering that explanation until it sinks. When it sinks, then go back and check the code again to understand how they relate. All right. Cocktail sort. We're going to use children that are in line again, that we're trying to organize. You walk from your left to right. You know, in assembly ground now, what do? You have so many lines, right? Okay. Swapping children if they are in the wrong order. Then you walk now from your right to left, doing the same thing. You keep going back and forth until everything is in order. Can you see that this one is moving from left to right, like you are shaking something? That's why they call it like shaking a cocktail mixer. You know, you shake from left to right. Exactly. So you walk from left to right, you swap the children if they're in the wrong order, you bring the one that is small to the front, and then the one that is big to the back. Then you walk from the left to the right, doing the same thing. You keep going back and forth while doing this until everyone is in order. Remember what I said? It's like shaking a cocktail, right? You are moving things in both directions. Okay. Now, let's go and look at the visual representation of cocktail. I like the word cocktail, but this is cocktail sort. Okay. Now, cocktail is sweet, so you should enjoy this cocktail sort as well, shouldn't you? All right. Okay. Let us now go again and check the visualization. Let's look at it. Remember, It starts from the left, goes to the right, and then it will come back again. It will come back to the left again and keep swapping, keep swapping. So when it sees that, oh, this one is smaller, it switches it to the other side. And then it goes back again to the right, swapping each one of them. So as it is doing it, you will see that by the time it gets to that end, it will put the one that is smaller. And then once it's done to the end, can you see that the last place is now stopped is the third bar from the right? Okay. And then it keeps switching back again until everything is sorted. Now, let's take a good look at the code. All right. Now, how does the code work? It checks if it is running. The starting point is 0. It sets an end point as well so that it will know where to end it. And it also have a swap status, a Boolean value of swap, true. And while it is swapped, once it gets to that stage, what does it do? It sets that swap to false immediately so that you won't end up swapping it again. Then it now checks for I is that, and I is not less than the end value that we have set, it keeps increasing. If it is not swapped, it breaks. And it calls the end by reducing that index by 1. That's the essence of this minus minus here, by 1. Okay. And then it now creates another for loop that now checks if I is equal to n minus 1, then I is greater than start. And then what does it do? It reduces I by 1. Like I minus minus means I minus 1. Okay. And then it draws the bar and then sets the start value, increases the start. And if everything has run, what did it do? It will set the running to false. And that was why when it was done, the bar stopped running. Okay. Now that we have a visual representation of cocktail, let's go to the next one. Bitonic sort. This one is parallel friendly sort. And it works by building Bitonic sequences. All right. Like mountain range peak sorting. You can imagine mountain range peak sorting, like the peak of mountains. That's what you are sorting. And it's best for GPU and hardware implementation for those who are doing computers, building our laptops that we're using, kind of. And it works for non-power of 2 data. The time complexity here is what? 0n log squared n. Can you see that? Even even the stuff alone is interesting. I am reading a chat from Edit and it said it's lost. Don't be lost. Don't worry. Try to look through again after the class and try to just listen to the explanation over and over until it sinks. All right. Now, as usual, I'm going to try to explain what the visual representation is. Okay. What do we do here? Let me try to explain Bitonic. Bitonic sort. Here is like organizing a line of children. First, we arrange them in special pattern, up and down. Then we keep splitting the line in half. We sort each half separately. Remember the way we did merge sort? All right. We keep doing this until everyone is in order. Now, let's take a look at these visuals. I'm going to reset it. Okay. Just have a moment to look at it and see how the flow works. You will see that it keeps moving and doing the sorting. Can you see it separates it? From the explanation that I did earlier, we will realize that what it is doing is what? It keeps splitting the line in half. It sorts each half separately, and it keeps doing this until everyone is in order. That is simply what it's doing. Okay. Now, let's go to the code and see what Bitonic sort looks like in the code. Let's take a look. All right. We can see here that what? It checks if it is running. That's the first thing we always check. Is it running? Okay. It now sets the number. It will always set the number. Okay. Then we're trying to get the next power of 2 here. And then you're trying to find the maximum safe integer and the padded array. And of course, we call the recursive in here, where we call that function in itself over and over until it fulfills this condition here. And then once it is done, it merges those values together. And that is simply Bitonic merge. It's already the advanced application of the other sorting algorithms we have been talking about. Okay. Now we're moving on to the next one, which is the non-comparison sort. Okay. For this non-comparison sort, the first one we'll consider is the Radix sort. This one does not sort by comparison, comparing one and then no. This one sorts by digit and character. It is best for fixed size keys, either numbers or strings. And the time complexity is ONK. In this case, the K is the length of the key. Okay, as usual, I would like to explain again in a simple format. This time around, we'll be using cards to explain. All right. Now, Radix sort is like organizing a pile of cards with numbers. Remember those cards we talked about earlier? Okay. Now, the first thing we do is to look at the card's last digits. So, you know the card has a number. We're not looking at the last digit of each number. Then we put all the numbers with the same last digit together. Can you see that it's way different from what we're doing before? Now we're talking about digits, and that's why we say it sorts by digits and character. Then we look at the second to last digit. We put all digits with the same second to last digit together. Remember how we used to do tens and hundreds, right? What do? You look for the tens, you look for the hundreds, you look for the thousands. And exactly, we're doing something like that here. Okay. We keep doing this for each digit position. When we are done, all the numbers are in order. This Radix sort is what we use for addition in primary school. When they tell us add tens together, then when you have tens, if it becomes 100, then add it to the hundreds that you have, then add it to the thousands. It is just the same thing. So when you understand that logic, the process of adding and checking is the for loop, and seeing, okay, is this still a tens digit? That process of is this still a tens digit is like saying, while this thing is tens, do this. If not, once we don't have tens again, what do? Move to hundreds. For each thing you do, keep adding one value to it. And now I've talked about the while, I've talked about the for loop, and that is how this thing is being converted into code. All right. Now, I would like to do a visual representation of the Radix sort. Now, let's look at this Radix sort. Okay? Let's reset to ensure we have random numbers, and then try to start it. Now, what this thing is simply doing is it is looking at the last digit of each number and then putting all the numbers with the same last digit together. Once it is done doing that, it goes ahead to look for the second to last digit of each number again. and put all those numbers with the same second to last digit together. And it keeps repeating that process until it is done adding all the numbers in that order. That is simply what Radix sort is. So it goes from beginning, and that's why from beginning to the end you have while it's getting this value, do this. For each loop that it has, while I is less than the length, which is this last one, the last one will be like the length, how you can get the length. So that is how it is getting where to end this search. All right. So, and it keeps looping through like that. Can you see that this one is taking a longer time compared to ON? So it's that, and that is why we say each one has what it is best for. This space complexity needs extra space for the count array. It also needs extra space for the output array. Can you see? So because we're dealing with NK here, so you have to consider both of them. Okay. Now, each sorting takes ONK time. But then the total sorting itself will now be the number of digits in the largest number times NK. Can you see how interesting this one is? Okay. Now, that is how we can sort out this particular one. And you can see gradually it is forming the set. And now it is done. You can see the last one, the red bar, is on the last part. Okay. Now, I would like us to go through the code. It sets the maximum bar from here. We can see that the length of the bar, it gets it. And then what happens? It creates a new array. And then it fills that array. And then it counts the occurrences of each digit. And once we are done with that, it now calculates the cumulative count using for loop. And then it builds the output array from the right to the left. And that's why you see that you will notice that that bar was tall at the right side, and then it was reducing to the left side. Okay. And it copies back the original array. And this is the Radix sorts, and this is the counting of the Radix, where we are using here, right here. So at this point, we'll be going to the second non-comparison sort we'll be talking about today, which is the bucket sort. Now, this bucket sort, from the word bucket, it distributes elements into buckets. It is best for uniformly distributed data. And the time complexity is ON plus K. All right. Now, let's try to do a little explanation of this bucket sort. Now, it is like organizing a big box of toys. Okay. Now, this bucket of toys, this big box of toys, what happens? The first thing we do is to make different boxes for different sizes of toys. Can you see that this one is like categorizing them based on their sizes? So, in a situation where you have small boxes, you do what? You make a box for small boxes, you make a box for small toys, you make a different box for medium-sized toys, you make another box for large toys. We look at each toy and put it in the right box. Then we now sort the toys in each boxes. Finally, we now take all the boxes and put them together. So it's like you're first of all categorizing them and then sorting them based on that category that you have put them. And once you are done sorting those categories together, you can now make them. Okay. Now, let's have a look at the visual representation of the bucket sort. You will see that the style is totally different from what we have been seeing in the comparison type of sorting. All right. Now let's go to the last sorting for today. Oh, before we go, I would like to show you the code for the bucket sort. All right. And here it checks for the length of the bar and times it as n. And then it sets the bucket to be the array from the length. All right. Can you see that we're making use of bucket here? Then when you are writing your code, ensure to name it a word that is familiar to the functionality so that when people are looking at it, they understand it more. Then it sets the minimum and maximum value and sets the range, which is always the subtraction of the minimum and maximum value. You're subtracting the minimum from the maximum value. And then it gets the bucket size, which is the range divided by n, which is the length of the bar. Okay. Now it does a for loop and then it sets the bucket index and it starts pushing the index, the value into an array. Now, after it is done with that, it set the index to 0 again. Remember, we're first of all putting everything in boxes. Aha. Now, we are now doing, the next thing to now do is what? Loop through them and then sort the bucket. All right. Now, the last one for today, which is counting sort. Counting sort counts occurrence of values. It is best for small integer ranges, and the time complexity is O n plus k, and k is the value range. And what does counting sort? How can we explain counting sort? Now, in this part, we are going to be talking about colored blocks. Okay, first we count how many blocks we have of each color. We look at, okay, red, how many do we have? Blue, how many do we have? Yellow, how many do we have? Then we make a special box with a space for each color. Then we look at each block and put it in its color space. When we are done, the blocks will have been organized. You know all these games that they used to do. These are actually games that people do that we watch every day, but we don't take it into what happens is that when you look at it like that, you realize that it is what we use on daily basis. All right. So what we can do here is take cognizance of it and then try to process it like how would this code look like. Now you can see what counting sort is. It's simply taking blocks or balls and putting them in boxes, which we have seen. In fact, it's inter-house sports. Most of the inter-house sports have this counting sort. Yet we find it hard to understand what this is, right? Okay, so now after doing that, let's try to see the counting sorts. We have 2 minutes to go. Let's try to see the counting sort and see how it works. Okay, let's reset and start. It just picks and then it checks it. And then it does it, and then that is it. So it picks it, it checks for the value, it goes. So now let's take a look at the screen and see these ones. They're actually worst scenarios, right? They need extra space for the count array. They need extra space for the output array as well, because you are dealing with NK. So it's not, if you don't have space, you cannot use this kind of things. Because we have talked about worst scenarios and good scenarios before, and that's why we don't need to keep repeating. If you notice, you see that they follow similar pattern. Yes, some have the same time complexity, right? It's just like we are different humans, right? But it's either you are from Africa or from Asia or from Europe. Do you understand? But they are different human beings. That is just the same way time complexity has to do with sorting. Okay, and our time is up now. And I hope I've been able to answer some questions. And okay, the next class is data structures, array, hash table, and linked lists. And it's going to be a building block on what we did today. So please ensure you go through your classes and study and read well and try to understand that explanation. Don't focus more on the code, focus more on the explanation and how it works. Once you understand how it works, looking at the code, you would understand the code when you know how to start writing code. All right. Thank you, everyone. And that will be the end of today's class. I hope you have enjoyed it. Do well to go through your classes and study. Thank you, and do have a nice time. Bye-bye.